Welcome back, guys. This is video 4 of the Chapter 14 lecture on Mendelian inheritance. This hopefully will be a quick one. So for any character, dominance and recessiveness depends on the level at which we examine the phenotype. So if we look at Tay-Sachs, the disease is fatal, but at the organismal level, the allele is recessive. So so at the biochemical level, the phenotype is incompletely dominant. At the molecular level, the alleles are codominant. So depending on how you look at this this disease, is it dominant? Is it recessive? It depends. So at the organismal level, like as an organism, once I receive, I have to have 2 copies of that for it to permanently damage me. But at the biochemical level, when you zoom in, it's incompletely dominant. So you've got a mix. Remember, incomplete dominance means they blend. So the biochemical level, again, is going to be the enzyme activity, which means I can't break down the lipid. So I'm kind of going to be able to break down the lipid at the biochemical level. I'm not going to be able to do it well. I'm going to be able to break down some lipids. And then at the molecular level, the alleles are codominant. I hope that makes sense. I feel like I stumbled through it the first time, that's why I went through it a second time. Cystic fibrosis, that's kind of another example. Going to go through that one quickly. Recessive patterns are usually rare. They tend to skip generations. Definitely increases in consanguineous marriages or matings, which you might call that incestuous matings, same blood. Maybe you've heard about the blue people of Troublesome Creek. If not, you will soon. Dominant disorders are definitely less common than recessive. Sorry about that typo there. There are a couple. They're less common because if they're dominant, they're expressed, which makes the individual less fit. They don't tend to be passed on as frequently as do recessives. So each individual had one affected parent, doesn't skip generations. Homozygous cases do show worse phenotype symptoms, so that indicates a little bit of what we were talking about a few minutes ago, where maybe there's some incomplete dominance going on at a lower level. So there's a dominant example. Dwarfism is a dominant allele, so it's certainly possible for dwarf parents to have quote-unquote normal-sized kids. And there's our inheritance pattern of that. So genetic screening. Risk assessment for inheriting an individual inheriting a specific trait. We're going to use probability to calculate that risk. Here's kind of the general formula. Basically, you take mom's probability, multiply by dad's probability, and then multiply by the disease risk, which you kind of got to be an insider to figure out what those are. There's a table that helps you kind of figure that out. So here's an example. Wife has an albino parent. Husband has no albinism in his pedigree. So what's the risk for an albino child? Logic here is my wife and I both have some family histories of things. When we got pregnant, we went in, we had a basic screening done, and then we had some conversations about, do you have this in your family history? Do you have this in your family history? Okay, we need to have some conversations, because if our child is going to be born with a genetic disorder, we need to be prepared for that. We need to be emotionally prepared for that, because it's going to be a shock. And we need to be physically prepared. We might need to have medical equipment. We might need to have, who knows, therapists lined up. Who knows, depending on what the risk is. So that's what this is kind of gearing towards. Should you have the baby or not? Or maybe it's before you decide to get pregnant. Are we a good fit to have a baby? So in our example, the wife has an albino parent, so the probability is 1.0 that she has the allele, because albinism, remember, is a recessive trait. So she has that allele. The husband, the probability is near 0. It's a recessive trait, so risk is heterozygote times heterozygote 0.25. But the husband doesn't have it in his family, so the risk is 0. But if you assume that the husband is a carrier, which is kind of the worst case scenario, right? Then there's a 0.25 chance that any child will be albino. Now remember that these are probabilities. It's not like one child influences the next child. Every time there's a 0.25 opportunity. The next slide says that same thing too. There's the Punnett square that shows that. Yeah, so the risk is 0.25 for each child, not dependent upon the last child. So it's not as if you have, okay, so the risk is 0.25, so, or 25%, so we only need to have 3 kids. The first 3 will be the healthy ones, the 4th one will be the sick one. That's not how it works. So once you have that information, then you can have the conversation. Okay, so now we've got a risk between a 0 and a 25% chance. What can we do as the pregnancy is progressing to identify, again, do we need to be prepared? Did they inherit it, or did they get the 75% chance of being healthy, or being not albino? You know, in that case, there's nothing major that you would have to have. But if you're talking about Tay-Sachs or something like that, it would be a big deal. So then the next thing, there are options. You can do chorionic villi sampling, you can do amniocentesis, you screen the newborn. In terms of fetal testing, what they'll do is they draw mom's blood. They have mom pee in a cup constantly, and they're looking for different things in mom's urine. They're looking for extra sugars to see if she has gestational diabetes. They're looking for things that are coming to mom through the through the baby's umbilical cord, things along those lines. Then they also, if they do an amniocentesis, they're going to reach into the amniotic fluid. They're going to draw some of that amniotic fluid out. You see that has to happen between 11 and 14 weeks. And they're going to basically make a karyotype. They're going to do biochemical tests and do some things like that. But they can build a karyotype off of the liquid, the amniotic fluid. So like people have this horrific image in their head of this massive needle going in and poking the baby and drawing out some of the baby's cells. That it's not going into the fetus. They're drawing out that amniotic fluid. Then they run some tests on it, again, glucose levels, things like that. And then they're going to karyotype it, and that's where they can see if you've got a chromosomal abnormality, or maybe you've inherited Down syndrome or something along those lines. Between 8 and 10 weeks, they can do chorionic villi sampling. They're going to extract tissue from the placenta. There is a greater risk, but you get information quickly. So that's tends to be, if you're high risk for something, like if you had a 0.25 risk for something, you probably would not do chorionic villi sampling. But if you had like a 75% or something higher than that, maybe that would merit taking that risk. Of course, we know what a karyotype looks like. And then once the baby's born, they do all kinds of tests on it immediately. I can remember when my son was born, they give you a few minutes with your baby, and you bond with the baby and all those types of things. But then quickly, like within minutes, they take a blood sample, and they're instantly running tests. And the reason that you can't leave the hospital for 3 days is there's a blood test that comes back 3 days later. And when that blood test comes back, if you're healthy, you go home. If you're not, you got to start treatment on some pretty specific things right away. They tend to test they tend to test blood quickly because your genotypes are not ever going to change. So if you pick up that recessive trait in minute 3 of that baby's life, then you can treat from minute 3 of the baby's life. You don't have an accumulation of harmful impacts happening for 2 years, 3 years, 4 years, however long it would take for those symptoms to manifest themselves. Required by law in all states, even if you have a home birth. To go to the hospital, you have to have newborn screenings done. Tests 1 to 6 conditions depending on what state you're in. So getting close here. Multifactorial diseases are things where the genetics and the environment interact. Think about diabetes. You've got a genetic predisposition, and then you either eat like crap and continue on your path towards diabetes, or you are super healthy and you control that. And you don't become diabetic. That's the word I was looking for. So there are some examples. Heart disease is one. You could get it from genetics, sorry. You could get it from your diet, from having a terrible diet. You could not exercise, or you could get a bacterial infection. Probably to get heart disease, you have a little bit of all of this going on. But if, again, like I said, if you can get a genetic screen on minute 3 of your life and you know you have a genetic predisposition for heart disease, your parents and yourself, you can take care of these 2 things. You know you're already on the path to heart disease, so maybe sugar's not for you. Maybe you need to be an athlete. Maybe video games aren't for you. And then a bacterial infection, if you have a risk, you probably are going to be somebody that goes to the hospital a lot. An example from plants, these are hydrangea. If there's iron in the soil, will be blue. If there's no iron in the soil, they're pink. I figured this out the hard way a few years ago. I bought it's called a blue moon hydrangea. I spent too much money on it. And I planted it, had these really beautiful blue flowers, and then the next year they came up and they were pink. I said, what happened? How did my flowers change color? I think I know a lot about genetics. What the heck? That shouldn't be able to change. Well, I talked to a master gardener, and they said, just take an iron nail and drive it into the ground right next to your plant. 2 weeks later, the flowers were blue again. So again, the genetics of the plant are part of the equation. The environment surrounding the plant is the other part. So, finally, in summary, know the Mendelian crosses and their patterns. Like I said, it is helpful to memorize that. Be able to do Punnett squares, be able to do dihybrid crosses, focus on the vocab. That was a big weakness for us in the fall. Be able to interpret pedigrees, be able to create pedigrees, and then be able to work with some of those common trait examples. That'll be a piece of cake with the inquiry. So finally, that's the end of Chapter 14.